Okay, so I've got here what I'm calling example 4.3, water rocket launched vertically. And this example is going to be a little bit different than the other ones because I have a few goals that I want to accomplish. And so one of them is, this is a little bit more of a design question here. I'm going to focus a little bit more on the design side of things, and try to make it a little bit more like the types of problems you might want to solve in practice. So that's one of the goals. Another goal is that I want to use a spreadsheet. So I want to really walk through here and show you how you can use a spreadsheet, especially when you have like design type problems and how they make the work way easier to solve. So just how powerful these spreadsheets are. And the final goal here is I want to bring together all of the material that we've covered up until now, because a lot of the examples tend to be very specific on like one section or another. And I want to show in this example, we're going to pull together a few different things we've learned to solve out this question. And this is the kind of thing where the water rocket in this question, you could actually go design and build one and then sort of test out how well your calculations reflect what actually happens with the rocket. Okay, so basically the way I frame this question is to say, okay, we've got a water rocket made from a 2-liter pop bottle. We're going to launch it vertically in the air. So what we're going to do is we're going to fill it with water and then pressurize it up with air from a bike pump. I've listed a max pressure there that the system can withstand. So that's 80 PSI or 550 kPa. And then just a little question there. So what we'll want to calculate here is like, how can we set this thing up so that we attain a height of at least 150 meters? And then we're also going to look at some plots of the height over time. And so just so we're all on the same page, I'm going to start by showing here an example video of a water rocket. You may already know what that is, but let's just have a look here. So this video is from iCreatables, and I actually had a capstone group build one of these for me. So I'm hoping to be able to use it to sort of demo this calculation and see how it works out. Okay, and now in a design question like this, where we're going to start is to look at like, what are the variables that we can control? Because oftentimes in questions, we just give you everything, right? But in this case, I want us to reflect a little bit on this question. So when we've got this rocket set up and we're about to launch it, the variables that we can control are, we can decide how much water to put in it, right? So how much we fill the bottle with water. And then we're also going to pressurize it with air from a bike pump. So we've got a limit there, 80 PSI. We probably don't want to go right up to that limit. So we get to decide how much we pressurize it. So I'll write the amount of water as like the mass initially of water, okay, and the initial pressure, where the initial values, I'm going to put this subscript 0 on those. So we know that that's the initial value. Okay, now we're basically going to walk through this calculation and figure out what those values need to be to give us this height that we want. So first things first, I'm going to open up a spreadsheet here and start by putting these values in the spreadsheet. So I got my screen open, and what I'm using here is Google Sheets, but it's very similar if you work in Excel or Numbers or other spreadsheet programs. And to get to this, you just literally Google like Google Sheets and it'll open it up. And the nice thing about these Google applications is they can be shared and all that stuff too. So put some headings here so it's well organized. We always want to keep the units, right? Okay, so I'll make those bold. And we don't have to put values in for those just yet. Okay, now what we're asked to calculate here is the height, how high it goes. And we've done a previous rocket example, and so we know we can use the force balance or our momentum equation to get information about how the rocket accelerates, right? Which will lead us also to information about the velocity of the rocket and therefore also the height of the rocket. So that's the equation we're going to use here. I've got it written like the exact same way as the video. And that's the complete form there, but we don't need all these terms, right? So let's go through and cancel them off. So we'll start with these external forces. We've covered a lot of material up until, the end of section 4 here, but we still haven't looked at air resistance or drag due to friction. So I'm going to still set this term equal to 0, but we know that there will be some. So that's just an approximation for now. And I'll label that clearly here. Now we've got the body force term. We're going to solve different equations. So I'm going to give each equation its own color so we can be clear about which one we're solving at which time. And we've seen that this is mass times acceleration due to gravity. CV's control volume. Negative g mcv. I'll actually explicitly draw the coordinate system on this. Gravity's acting downwards. We've drawn y as positive upwards. So we'll write that as negative g mcv. Our next term there is the acceleration of the control volume itself. That's the important one. That's the one we want, right? That's the acceleration of the rocket. So we have seen this before in the rocket question. So if you wanted more detail, you can go check that out. When I do it here, I'll do it with a little less detail so we can move through it a little bit more quickly. So I substrate in here and we have the acceleration, and then solving out that integral, integrating the density over the volume, leads to total mass of the control volume. Okay, this next term is 0. This is where it pays to know what these terms mean, right? So that term's referring to the rate of change of the momentum within the control volume. And so we don't have anything within our bottle. We don't have any momentum changes with time. Momentum is mass times velocity. So that what that means is like within the rocket over time, we don't have any abrupt velocity or mass changes where they change dramatically as time changes, right? There's just water in there and it's flowing out. And I'll fill in our drawing a bit. So we're going to have some water. We get to decide how much we fill up that bottle. So have some water in there, pressurize this up to P0. That is our initial mass of the water. For the total initial mass, right, we'll just add the weight of the bottle itself to that value as well. And then our thrust comes from the velocity of that water exiting out through the opening, VE for exit velocity. Okay, so now the next term is the momentum crossing all of our control surfaces, right? So we can simplify this one. So the lowercase v is the velocity component in the y direction relative to our reference frame. So we are crossing this opening here. Okay, so that's negative VE because it's downwards, but we've said that y upwards is positive. Okay, now the rest of it, we should have seen enough times by now in other examples. Rho v dA, so v dot dA, it actually is Q, right? The volumetric flow rate flowing across that area. And the dot product basically gives us the sign that we need. Multiplying our volumetric flow rate by a density at the front there converts volumetric flow rate to a mass flow rate. So that term is going to be m dot E, and the dot product tells us the sign. And so the velocity vector, Vx, Y, Z, is VE, which points outwards from the area. So velocity is exiting, and the area points outwards as well. So that means it's positive. Outgoing velocities are positive. So when we sub that in, it's negative VE times m dot E. Okay, now to solve this, right, we got to take a closer look at how we get each of these terms. So G is a constant, the mass of the control volume, we can figure that out based on how much we fill the water bottle from our mass variable there. The acceleration of the control volume is what we want from our calculation, right? And now these aren't given to us because they wouldn't commonly be in a design question like this, right? We're gonna have to figure out how to get these. And what we know from our conceptual field of fluid mechanics is they're gonna depend on the variables that we control, right? So that how much water is in it and how much we pressurize it. Okay, I'm gonna actually label these equations. Okay, what we're gonna need to do is we pressurize this water bottle, right? So we need to know how you convert that pressure into a velocity. And we've actually done another example of this, right? So if we look closely at the bottom of the water bottle right here, it looks like this, okay, like a nozzle, right? And we can label the flow there flowing from like a point 1 to a point 2 along a streamline. And so you can probably see now what we would want to relate that pressure to that velocity. We could actually use the Bernoulli equation like this, just like we did in the nozzle question. So again, you can go back and look at the nozzle question for more details. I'm gonna go through it here, maybe with slightly less detail than I would have done in that first example. Okay, now we've made some assumptions, right? Bernoulli does not apply to every situation, although we'd want it to. And in this case, it doesn't match all the assumptions, right? Because we're supposed to have frictionless flow. And there would be a little bit of friction, but it's okay, actually. It's going to give us a good approximation. Like we know that about our design calculations, right? Like they're not going to be exactly the value we expect to find in the field. It's just going to be a really good approximation. Okay, so I'll simplify this a little bit. There's a very, very small elevation change across this bottle. So we'll neglect the elevation change because it's very small. And absolutely feel free to include that as well. And you'll see that it actually is inconsequential. It makes very little difference to the final value we get. And now V1 as well is going to be very small, but maybe I'll show you the calculation for that one first, and that actually is a nice way to use another equation we know. So what I want to show you is that V1 is actually quite small in this equation compared to V2. And so if you think for a second, how can I relate V1 and V2? Similar again to the previous nozzle question is we can use a mass balance because we know mass is going to be conserved as it flows through the bottle. So there's the equation there again from the video. So in our case, at point 1 of our control volume here, the velocity is entering and the area would have a normal pointing outwards, so that'd be negative. So it's the sum of all the control surfaces. So negative V1, A1. Point 2 there, the flow is exiting. It's the same direction as the area, so that's plus for the dot product, V2, A2 equals 0. I can simplify this in terms of V1. just rearrange it. The bottle is circular, so I can sub in for those areas. Those are both circular areas. So we can use pi r squared or pi d squared over 4. Simplify that a little bit before we plug any numbers in. Pi's cancel, 4's cancel. So we just end up with, and the values are given there on the figure. You can just Google that for dimensions of a pop bottle, right? Or I actually measured mine. So we sub those in, and then we get value of 0.033 V2. So V1 is quite a bit smaller than V2. We can see that. Not only that, this term here that I'm going to cancel now. So if you actually left that term in the equation, you would have to square it. So when you square it, you get 0.0011 V2 squared. So it's way smaller than V2 squared. So what happens if you sub it in, you'd end up with like 0.999 V2 squared, and you can just assume that that's 1. So what would happen is if you included that value, you would end up just canceling it off anyways, because it's way smaller. Okay, so again, feel free to do that in a few more steps there if you want to prove it to yourself. I'm going to go ahead and assume it's 0, simplify our calculation. So when that's simplified there, we end up with the following, where P1 we'll say is our P naught pressure. At P2 we have P atmosphere over the density, and that V2 of course is our exit velocity, so I will write that there. So there we go. So we've already answered our question. So how do we get these terms? Well, we've just gotten the exit velocity there because we can relate it to the pressure that we pressurize it at. This is getting a little crowded, so I'll use a fresh page here to show you how we do the mass flow rate. Okay, so for mass flow rate, we've seen this quite a bit now, and we saw it just on the previous slide as well. Okay, so we know the exit velocity and we know the area at point 2, so we can then just sub in for that. And now we can do this in our spreadsheet. Okay, so I'll label this over here. Calculations we'll do over here, just to keep our spreadsheet organized. And we're gonna need a few more variables. So for the velocity equation that we had there, we have a P naught in it. We have the surroundings, so P atmosphere, do that in pascals as well. Density of the fluid, rho. That one we can sub in because that's a fluid property. We'll say density of water is 1,000 kilograms per meter cubed, and we're going to need the diameters as well, and the units we want is meters for that. Okay, so let's go and sub in here for VE. So we just calculated that, and this nice thing about doing it in a spreadsheet is that you don't have to worry about messing around with your calculator. So we'll do equals square root SQRT is the function for that. The equal sign denotes that you're putting a formula in and it has to actually solve it. Then you use brackets for what goes inside. And actually you can see Google Sheets is showing you there how to use that function. And so the value you want the square root of, in our case, it's 2 times, and then you can just take the values. So we're gonna put the value for P naught here, right? So I take that one, I can just click on it and it puts my cell there, it's cell B3, okay? And then I'm gonna minus this cell here where we're gonna put the P atmosphere value. So I click on that and it'll do that for me, it's B4. Okay, another bracket to make sure it does the math correctly. And we're going to divide by the density, the rho value, which is right there. Finish off our brackets and then push enter. Now we don't have all the values entered there yet, so it's not going to give us a number just yet. Now I also want m dot E, and so for that I'll do another calculation here. I'll actually do the area calculation first, which is, we've already seen that, pi. I'll show you how to use pi here. So you can just do pi and then curly brackets will give you the pi value, and it says the value there for you. So the spreadsheet will automatically put the actual pi value in when they calculate it. Pi times, this is area 2, so we want the D2 cell there. So that I click on that one that I want, squared, and then the whole thing divided by 4 will give me my area, and that's going to be in meters squared. And actually we can fill in, we know these values already. This was 11 centimeters, so 0.11 meters, and this is 0.02 meters. Okay, so there you can see it's calculated it for us. Now I'm going to reduce the number of decimals it put there. We don't need that many decimals, we'll just keep a few of them there. Okay, and that's this button here, decrease decimal places. Okay, now I can do m dot E. I'll just call it that. There's nothing special about that. It's just so I can name it, I can remember what I'm doing. And the equation we have for that one is equals rho, which is here, right? Click on that cell, times, and then VE. It's gonna calculate that up here, so I can use that value there. So I click on that cell, right? Puts in F3, and then times area 2, enter. Okay, and that's gonna be in our units of kilograms per second. All right, and that's 0 for now just because we haven't put in all the values here. I can actually put in P atmosphere, right? 101, 325. No, it doesn't like that. What I'm going to do here, just so it actually punches in some values, is let's just, for now, for the sake of the calculations, let's take the value, the max value, which was 550 kPa, so 550,000 pascals. And let's just imagine we're going to use, just for now, we'll play around with this later, right? That's the beauty of a spreadsheet. But let's just say we use about 3/4 that value. Okay, so I'll just multiply that by 0.75, okay? And the initial mass, we can enter a value for that. And we know it's a 2-liter pop bottle, right? So I'll just do a quick calculation here. So we wanna know how much mass would be in the 2 liters, right? If the bottle was full, let's say, for example, we know the density of water is 1,000 kilograms per meter cubed. So let's convert that to liters. And this, again, you can just use Google to do your conversions if you want. So we can just say like meters cubed to liters. It's going to tell us that. So, right, so 1 meter cubed is 1,000 liters. So we'll sub that in. So we have 1,000 kilograms for every 1,000 liters, which actually means we just have 1 kilogram per liter. Okay, so in a 2-liter bottle, we could fit 2 kilograms of water. But again, let's say to start with, let's just imagine we're going to fill it half full. So I'll just put that in as 1 as like a starter value. And as I mentioned, we'll go back and revisit that. That's going to be part of our design we're going to look at later. Okay, so for now we have an exit velocity and m dot e. So now we can go back to our momentum equation and finish solving that one out. Okay, so I'll rearrange it. I'll use the turquoise color again. So we're going back to that equation from above. Okay, and I'll just drop in the equation we had before so you can see it again. Then I'll rearrange it for the variable that we care about, acceleration. Okay, so that's the acceleration, but we know, again, from our previous rocket question, we can actually calculate the velocity from that acceleration expression. And then from there, further, we can calculate the distance traveled from the velocity value, which is going to be our height. So let's go through and do that in steps here. So for velocity, same as before, the acceleration is the derivative of the velocity with respect to time. So we separate and integrate, and we can do a mass balance to get the mass of the control volume as a function of time. Again, for more detail on that, for the full steps, you can have a look at the rocket question itself. I'll write it out here. So the mass of the control volume, we know that's the initial mass minus the mass flow rate out of the bottom of the rocket times the time. Okay, and again, I do the complete steps. I do a complete mass balance on that in the other rocket example. Sometimes people intuitively can figure that out too, right? So if you want the detailed steps, check it out there. And then I'm going to sub that in and do our integral here. So now we can use integral tables for this, or there's also software online for this. You can go to the Wolfram website and they'll integrate it for you. I like to use the integral tables. And so when you integrate this expression from 0 times 0 to time t, we don't need the constant if we do it that way, because we know we're at 0 velocity at time 0 being like the moment of launch. So that's our velocity expression there, and it's a logarithmic function because we've got t in the denominator. That again was from our integral table. Okay, now for this example, I think it might actually be helpful to specifically show you how to solve a few of these integrals and show you one of the online tools you can use to do this. So I'll search here for Wolfram Alpha, and then I'll click on calculus and analysis just so they can give me like a framework for what I want to solve. So I'm computing a definite integral, so I can just click on this as like an example, and so it gives me like a start point to work from. And then what I want to integrate is actually VE, I'll write that as V times M divided by, and then in brackets, capital M naught, I'll just write that as M minus lowercase m times t. Okay, and we want to integrate that with respect to time, so dt, and then we'll go from time, I'll just change what they gave me here in the example, from time 0 to time t, and I'll push enter. Okay, and there's your answer right there. So right here is the answer that it's given you on Wolfram Alpha. And as I mentioned, there's a few tools you can use to do this. So use whichever of these online tools you prefer, or you can use a set of integral tables like I do and solve them by hand. Any of those will work. What I'm going to do is I'm going to take this on a slide here and just show you how that simplifies to what I wrote, because I used an integral table to solve this. And one thing to note as well is when they write log, I've written that as ln, like ln. And so they say here actually that log x is the natural logarithm. So you can see that they're actually using that log to mean ln. Okay, so I'll just simplify this expression that I've taken from Wolfram Alpha here, just so you can see that it's the same as the one that I've written out. So this actually equals negative v, so that's actually VE. I just didn't put the subscript on, so it was easier. And then we've got ln, because log is the same as ln. So they're writing log base e, which is the same as the natural logarithm. And then if I simplify what's in the brackets, a 1 is just a capital M over a capital M, so I can write it out, and I'll put the not subscript on it, minus m dot e, right? So this is, I'll write it as m dot e, this I'll write it as m naught, and this I'll write it as VE, and this log is actually ln. Okay, so when we go through and I substitute it all back in, this is an m naught on the bottom there. So I have the same expression that I wrote in our solution. Just figured it would be nice to show you exactly all the steps for that. And now we just remember that that expression only applies, so that's only the velocity before the water runs out. Okay, once the water runs out, there's no more thrust anymore. Okay, so we assume that until the point that the water runs out, we would keep roughly equal pressure in the bottle, because that's the air pocket that has the pressure there. It's not exactly what happens, but it's a good approximation, and therefore our exit velocity would remain the same. Okay, so once the water runs out and there's no more thrust, we have a different force balance. So we got to do that calculation separately. So I'll just write at the side here, we want to figure out, firstly, when does the water run out? So to figure that out, we would have the initial mass of the water, and we have our given mass flow rate. So we want the time where that's equal. So the time, we'll call it TRO, that multiplies by our mass flow rate to equal the total mass of water that we start with. So I can rearrange that. So that's the total mass divided by the mass flow rate. Do our units work out? So that would be a kilogram divided by a kilogram per second. So the kilograms cancel in the seconds. Comes to the top, so that'd be units of seconds. Yeah, so that works out. So let's go back to our spreadsheet for our TRO, time that it runs out, and this is equal to our initial mass of the water that we have up here, divided by our m dot e, which we just calculated. I click on that, and now I push enter, and that gives me the value there. So I'm actually gonna reduce the decimals in all these so that they're easier to look at, so I just decrease the decimal places. Let's just keep a few there. All right, so that is in seconds. All right, so the water runs out in 0.13 seconds. Very, very quickly, the water runs out. Okay, now what would the velocity be right at the point where the water runs out? Well, what we would do then is sub in for our velocity expression right at the point where the water runs out. And so we can do this in the spreadsheet as well. And so first, we look at the variables there. We have most of what we need, except for m naught, right? Because that's the total initial mass, right? The total initial mass, not just the mass of the water. So we're gonna put mass of the bottle in here. And again, I just Googled that, and it says it's 54 grams, or 0.054 kilograms. And then my total initial mass is just the water that we start with, plus, and I'll click on the bottle cell there, right? And that is in kilograms. Okay, so that's what we need to calculate our velocity at the point that the water runs out. Okay, so that equals negative VE times, and now it's gonna do the ln for you as well. See, the spreadsheet's great, right? Like, you don't have to muck about with your calculator or anything like that. The ln of, okay, so we've got our total mass minus our m dot e times. So for times, I think you've noticed right now, you use the asterisk. Whoops, not t, we want this value here. Then divided by our total mass. The divided by is the slash there, another bracket, and then we subtract g. So what I'll do is I'll put g down here. So I'll put g there. So I'll click on it for now. Times, again, our TRO, enter, and I will put the g in here where I just clicked on it, 9.81 meters per second squared. Okay, that gives us a value of meters per second. So it gets up to, wow, like almost 73 meters per second in 0.13 seconds. Thrust is powerful. Okay, that's great, but we need the height, not the velocity. Okay, so I will use a fresh slide for this. Okay, now same as we did before, we know that the velocity is the derivative of the position with respect to time. So we're gonna have to do this in 2 steps again, right? So we're gonna have to figure out, like, what's the height that it reaches before the water runs out, okay? And then we'll look at how much more height it gains after the water runs out. So I rearrange this and I sub in our expression for VCV that we have right above there. We'll take our integrals from time 0 to time t, and again we know that the height, we'll set that initial height as 0. Now what I did was I used an integral table and I simplified this expression here to be the ln of that. I just simplified the denominator there, I rearranged it, and then found that expression in a table and then just simplified for it, and I got the following. Okay, so we'll do it in Wolfram Alpha again. So here's what I had last time. So instead, I'm going to replace this with our new integral. So it's a negative, and then it's ln of 1 minus m dot e over m naught times t. I'll just write it like that. And then dt from t equals 0 to t. Okay, so push enter on that. So it's solving now. Okay, and there's our solution right here. Okay, and again, log is the natural logarithm, so it's the ln, what I write as ln. And then I'll take that over to the slide and then again show you how it simplifies to the answer that I had. I used a table for this. I just want to demonstrate how you can use the online tool so you like explicitly see all the steps here. Okay, so I'll simplify this to what I wrote. So we had the VE out in front here in our expression, and so I grouped the VE and then had an m naught over an m dot e. And just a reminder, all these m's are actually m naughts, and these are actually m dot e's, and our logs are actually lns, right? And so I can multiply through everything by that. So I'll use a different color. So when I take this over here, if I simplify out these two terms, right, like I've done in the example below, I would be left with 1 minus, and then I would have m dot e over m naught times t, just so you can see that really clearly. Okay, so that's the substitution that gets us to the same one that I used. And then we had the same values in here. Okay, and then it was plus, because I have now that like m naught over m dot e from here, and we remember this like VE that's multiplied here would be like obviously out in front multiplying the whole thing. Okay, so then I would have to do plus m dot e over m naught times t. Okay, so those will cancel once it's multiplied through. And that matches exactly the expression that I came up with using my integral tables. Okay, and so I just want to make this point really clear. The only reason I'm showing you this simplification is just to show you that what I got with the online integral tool matches with what I solved when I used an integral table. And what I solved from the integral table is what I had on that other slide. So I've just copied that out and put it there. It's the blue writing there that you see in the box in the top right corner. So you don't actually have to do the simplification. It's just me showing you that the two match exactly. And so I'm showing you the online tool because it's something that you can use to solve integrals when you're solving these questions. It's probably like a simpler way to do it than the way I do it with the tables. So I want to just illustrate that for you here, so then you can go ahead and use that tool and solve your own integrals and just sub that straight into what I'm doing here. Okay, now we can figure out what's the height attained at the moment that you run out of water. Okay, and then we can find the expression for the height the bottle climbs after you've run out of water, which of course has a different acceleration expression and a different velocity expression. So firstly, let's look at what is the height reached when the water runs out. So we'll plug in this expression in our spreadsheet. So this is a bit of a longer one, so you can see me plugging it in here. This is the function line right here. So you'll notice as I plug it all in here, we're subbing in TRO. We want to know what the height is at the time that we run out of water. Just a quick note here to remember to use brackets so that all your algebra works out. It's going to follow bed mass, right? So you want to make sure it solves it correctly there. Okay, and I'll just again decrease. We don't need so many decimal places. Okay, so that's the height it reaches before it runs out of water. Now we're gonna have to do the equation after the water runs out. So I'll use a fresh slide for that. And again, similar to the rocket question that I did in a previous example, we know that after the water runs out and there's no thrust anymore, our equation just simplifies to the following. And when we rearrange that, we see that we just have this constant acceleration due to gravity. Same thing as before, so we know our acceleration is just the derivative of velocity with respect to time. So then we separate that and integrate that. And I've chosen to write this as a definite integral, as I've been doing throughout this whole question. So my bounds then, we have to remember that this flight behavior starts at the moment the water runs out. So that's why we have to integrate from our velocity at the moment it runs out to some current velocity. And then on the time side, we have to go from the time that it runs out to some time point. And that just leads to this. Then we can rearrange for our velocity, which is VCV. So that's the velocity of the control volume after the water runs out. Whereas the VRO there is referring to the velocity at the moment the water runs out. So now again, it's the height that we're after. And then once again, we just do that the derivative of that height with respect to time equals this velocity. And that's how we can get the height. So I'll use a fresh slide for that. And separate and integrate again. So we do those integrals, and then we have the following. I'll just rearrange that here for the height, so the y value of our control volume. Okay, now that's what we're looking for. That's the height that we need. But let's just do one more thing before we go back to our spreadsheet and plug this all in. What we want to know is the peak height, right? And so this is one more thing that we're going to sort of utilize what you learned previously, in physics or your math classes. So that peak height, or the maximum height, we remember to find the maximum of a function, we can take when the derivative is equal to 0. And we know that the derivative of our height with respect to time is the velocity. We've already used that fact in this question. Okay, so in this case, what we can do is we can calculate when is that velocity of the control volume equal to 0. That will give us our maximum height. And that makes intuitive sense too, right? Because when the velocity is positive, we still have the rocket climbing up into the sky. Then the velocity hits 0 the moment right before it starts to go negative again and drops back down, right? So that 0 velocity point is our maximum height. So let's do that. And now we can rearrange this to figure out what time does our maximum height occur at. Okay, so let's go into the spreadsheet and plug that in. Okay, awesome. So that's the time it will take to reach its max height. And then to get the value of that peak height, we can just take that time and substitute that back into our equation for the height, which is this one here. Okay, that's great. So we've got our value. That's our peak height value. But this is a design question, so we have a lot to think about. So now we're going to talk about what that means, and we're also asked to plot the height. So I'm going to show you first how we go about plotting the height of the water rocket. So the height value that we calculated there, the expression for that is a function of time. So what we can do to plot that versus time, in our spreadsheet here, we can just create a column that has all the time values, and then we have the peak height beside that, and then we can plot that. So I'll show you what I mean by that. So that's time in seconds, and I'll put the height in meters beside it. So for time, what we can do is, we know our equation is only valid for after the water runs out, that expression, the last expression that we had there. So we'll make this first time equal to TRO, okay? And then for each of the subsequent ones, what we can do in this cell is I can just take, so I can say equals the value of the cell above it, and then I'll just do plus like 0.25, let's say. So I'll go up by like a quarter of a second for each time step here. And then what I can do is if I just take this and then I'll drag this little box in the corner, I'll drag that down, that'll just continue to do the same thing. So it'll add 0.25 each time and it'll just span this whole time range here. Now for the height equation, I'll plug that in from the expression we solved for. And then when I put the t value in, I'm going to click on this cell here now. So each time it calculates this height, it uses the time here that's next to it in column I. Okay, now before I fill that down, I want to show you something here. So what we want to have happen is each time I solve for this height value, I want to use the different time that's in the column beside it here. So if I scroll down, it's going to fill all of those I2 values with each of the ones below it. But I want the other ones to stay the same. So what I can do is I can actually just put a $sign in front of the letter and the number. And what that means is when I scroll it down now, it won't change. So I'll show you in the cell there what I'm doing. Okay, so now when I pull this little box and I click on it, and I'll pull it down. So now what's happening is if I just click on this, you see these values with the dollar sign stayed the same, but the I2 now went to an I3, and then if I click on this next one, it goes to an I4. So the ones without the dollar signs will change, and the ones with the dollar signs will stay the same. Now I'm going to scroll down and plot this over a longer range of time so we don't just see the peak point there. I'm just going to tidy up here a little bit so we can see everything. So I'll just change the width of these columns here, so we'll be able to see these plots a little easier. Okay, now I'm also going to do the same thing here for the velocity. So that's something that we can compare as well. And so I'll do the same thing I did for time before. First time will be TRO, and then I'll just take each cell above it and add 0.25 seconds to it. Make these bold. Okay, and now I'll punch in that velocity equation that we have for after the water runs out. I'll just put dollar signs on these because we only want the L values to change as I drag this down. And one thing I can do as a little shortcut is just I can double click on that little square in the bottom right corner there, and that'll drag it down for me. That's just like an autofill. And just a quick look here to see if it all matches up. So we would have expected our peak height to be 273 meters at around 7.56 seconds. So that's pretty close right there. The closest time that we have is 7.63, and that's roughly the height we'd expect. And then we'd also expect at that time the velocity to be 0, and we can see it just went from being positive to being negative. So it would have been 0 right in there at about that 7.56 value. And of course, you can increment by whatever time step you want. I just chose a quarter of a second here just for demonstration purposes, but the beauty about the spreadsheet is you can do whatever you want. You know, you can increment by 1 second or 0.0001 seconds, so you can get as much detail as you like in a spreadsheet like this without really that much effort. That's another reason why it's great. So to plot these, I'm going to select the values that I want to plot. So I'll just click the mouse and drag over these values, and then I'll click this insert chart button here. Okay, it picks the kind we want. We want a scatter chart. Okay, and you can see the values in this chart editor that comes up at the right here. I like to get rid of the title because it takes up space, and I also like it to be roughly a square, and then I'm gonna drag this so it's not covering our data. Okay, and then scroll over, and now we look at that. So each of those blue circles is one of the height values that we solve for, so we can see that the water runs out very quickly, right? So in 0.13 seconds was when the water ran out, and that had hit a height of 2.59 meters. So what we're plotting here is only the heights after the water ran out. And so we can see this height versus time is what we'd expect. And it reaches that peak right around that 273 point there. So if I wanted to take this axis and edit it a little bit, I'll show you that here. So firstly, we don't need so many decimals. So I'll say we'll use a custom format, and we'll just use that number format there. And then for our grid lines, we can decide what to plot here. So they've got as default 100 meter steps. We can probably fit 25 meter steps in there. So we see now that gives us a little more detail. Now, if I want to do the same thing to the horizontal axis, I'll use a custom number format without all the decimals because we don't really need those. And same thing, I'll go to my grid lines and ticks, and this time click on horizontal axis there, and maybe I'll go by every 1 second, just so we can see a little bit more. All right, now that's what we were asked to do. Let me plot the velocity here, and then we can have a discussion about what this means and how as a designer we can actually use this data to make a better design, right? It's not just about getting numbers, it's about making this rocket do what we want it to do. Okay, so I'll click on the insert chart here. Same thing I did before. I like to have it roughly as a square. And we can see again that peak height point corresponds to when that velocity crosses the 0 line. I'll just edit these here so they're a little bit nicer to look at. And then on my grid lines and ticks, I'll just go by maybe every 5 meters per second. On the horizontal axis, I'll go by 1 second increments. And then on the vertical axis, I'd like it to start at a minimum value of -10, just so we can see where the 0 line is. Okay, now I'll close that, and we'll come back here and have a discussion about what the question is asking for. So essentially, what I want to know for this rocket, right? Like, I'm going to actually build one, and I want to make sure it goes high enough, but it's better if I don't have to use too much water or too much pressure, right? So I phrased the question to say, you know, like, what's going to give me at least 150 150 meters. So now that we have the spreadsheet all set up, we don't have to redo any calculations. It's all here for us, right? So if I take this value here that we can control on the pressure, I said let's do about 3/4 of the max pressure. Well, let's drop that even more. So that was 80 psi. So now we can go down, if we multiply that by 0.5, we can go down to about 40 psi. And you'll see that gets us almost the height we would need, 149 meters. And that's when the water is about half full. But I can play with all sorts of different combinations of these two values. So let's say I wanted to use a little less water because I didn't want to carry as much out to where I was launching it. Well, I can increase the pressure a little bit more. Let's say I raise this to, 60% of our max value, right? So that's 330 kPAs now. Well, now I would get 200 meters. So if I reduce the amount of mass that's in it, so if I put less water, right, then that water is going to run out a little more quickly. And let me try a few things here. So maybe 0.8 kilograms. Oh, I could go even lower than that. I could go maybe to 0.7 kilograms, give me about 157 meters. Okay. Now, you see, you can do whatever you want, and it's going to plot it for you. And I can even highlight this peak height value to show you that's the one we're looking for. So I can highlight it with like a bright blue value there. I can also highlight these two here, to remind ourselves that those are the ones we're changing. Maybe I'll make those like a green value here. And this is really why the spreadsheets are so powerful, because I can punch in different combinations of that. Now, another thing we got to keep in mind is that these calculations were approximations, right? We made a number of assumptions, most of which are pretty good assumptions, but they're still assumptions. Now, I think the biggest one that we made, right, is to say that there were no surface forces present, okay? Because we haven't gotten to the drag section yet, but we know there's going to be some drag forces on this. So that's going to reduce the values that we got considerably. So if I wanted to be on the safe side, right, I might aim to go quite a bit higher. So maybe let's say I'll fill it with the 1 kilogram, which is also 1 liter. And then maybe I will actually go up to, 3/4 of the pressure that it can handle, right? And that gives me 273 meters, but that's okay because a nice high flight will be great to show off this rocket. So I really want to overshoot the value that I'm aiming for there, just to make sure that with these assumptions, I still get the height that I need. And there were a few others, right? So we assumed the pressure would stay relatively constant within the bottle, but we know it's probably going to drop a little bit as the water's pushed out. We also used Bernoulli there, which assumes frictionless, and we know we would have some friction. So we would expect the height to be less than this peak height we calculated here, but this is still a really valuable exercise as an engineer, as a designer, to get a rough sense for what this height is going to be. And we can always improve the accuracy, like later, once we learn how to calculate the drag force, we can put that in here. And so by increasing the complexity, you can increase your accuracy. And so it's always a question of like, how accurate does it need to be? Like, is it really worth it? Okay. And so that's the end of that question there. I hope you've learned something about the design process and about, using spreadsheets to calculate this and how we can bring all the different sections of fluid mechanics together to solve a question like this. Maybe you're inspired now to go out and build your own rocket and fly it and see how high it goes. I'm hoping to do that in the future as well, to show how we can correlate, our physical rocket to what we've actually calculated here. And yeah, that's all for this example. So thanks for watching.